Yeah, I'll take a look. All right, for number 79, if we have pure methanol, what was the density of pure methanol? 0.7. All right. 7914? 0.7914 grams per milliliter. Okay, now what we're going to do is, what if we had pure ethanol? What would the density be? And so we're going to go ahead and calculate that. So the mass with ethanol is 33.470, and we know the volume. And so the mass is going to be 33.470 grams minus the mass of the empty pycnometer, which is 25.601 grams. 25.601 grams. And that's going to give us a mass of what? So 33.47 minus 25.601. Divided by the volume. What was the volume of the pycnometer again? So this comes out to 7.869. We're allowed 3 decimal places, so I'll carry 1 extra digit, which will be the 0 grams. And the volume was
9.9688 milliliters.
9.9688 milliliters. So 9.968. I think we're only allowed 3 decimal places, right? Or 4 sig figs milliliters. And so the density of pure ethanol divided by 9.9688 comes out to 0.7893, and we're allowed 4 sig figs, so I'll carry 1 extra here. 78936 milliliters. Since this is the final answer, I'll round it. 0.7894 milliliters. If we round this to 1 sig fig, could we tell the difference? No. Round it to 1 sig fig, they both come out at 0.8. If we round it to 2 sig figs, could we tell the difference? No. But if we have 3 sig figs of precision, could we tell the difference? Yes. Yeah, there would be different. To 4 sig figs, they're definitely different. So if we could measure these to 4 sig figs of precision, this is grams per milliliter, grams per milliliter, then we could tell the difference, right? Between these. All right, so this is what we're doing. Okay, so this is pure methanol. This is pure ethanol. But what if we have a mixture? We're going to have a mixture of methanol and ethanol. And so the question is this: can we tell the composition of the mixture based on its density? That is, could you tell me what percent methanol and what percent ethanol we have in here? And so the question comes up, we're going to have X percent methanol and Y percent ethanol. That's 2 unknowns. And so how can we figure it out? So I have a mixture of methanol and ethanol. What are the ways we can figure it out? One way we could figure it out is by measuring its density. And so this is the graphical method. Which one has a lower density, methanol or ethanol? Looks like ethanol has a little lower density. Do you see that? And so graphically, this is what I'm going to do. I'm going to make a graph like this. And at one end of the graph, I'm going to say I have 100% ethanol. If I have 100% ethanol, how much methanol do I have? I have 0% methanol. Here. What would the density be? This would be the density on the y-axis. The density will be 0.7894 grams per milliliter. Right? Okay, now I'm going to go all the way to the other extreme. What's the other extreme? The other extreme is 0% ethanol and 100% methanol. What would the density here be?
0.79.
Yeah, the density is going to be here 7914 grams per milliliter. And that's going to give me my second point here. Excuse me. So if we see a pattern like this, now the pattern is, what we expect is we expect a linear change in density. The more methanol we have, the more dense this mixture is going to be. And so we're going to assume it's going to be a linear trend like this. And that makes sense because it shouldn't be nonlinear. It shouldn't just skyrocket. You know, it should be a gradual change, right? And so if we have this, then we can come up with a law of the density of this mixture. What is the law of the density of this mixture? Well, the law is typically a simple empirical equation. An empirical equation is a mathematical equation that describes the trend that we see. And what's the mathematical equation that describes this trend here? Well, the equation of a straight line is y equals mx plus b. And so what is y? Y is the density of the mixture. The density of the mixture is going to equal the slope. Well, what is the slope? The slope is delta y, and so this is going to be 0.7914 minus 0.7894 grams per milliliter over delta x. Which one should we call our x? The ethanol or the methanol? We're going to just choose one. We're not going to use both. Which one do you want to do? Which one seems to make more sense? Should we use x from 100 to 0, or should we use x from 0 to 100? 0 to 100. So I'm going to use methanol as my x. And so it's going to be 100 minus 0% methanol. Methanol is abbreviated NEOH, capital M, lowercase e, OH. Ethanol is abbreviated ETOH. And so this is my slope times my x. What is my x? My x is going to be percent methanol, MEOH. Okay, plus the intercept. The intercept is 0.7894 grams per milliliter for the mixture. So let's go ahead and get the equation here. 0.7914 minus 0.7894 equals. Okay, how many decimal places am I allowed here? 4. So I'm going to have the density of the mixture is equal to 0.00200 divided by 100. Okay, the units for this are going to be in grams per milliliter divided by percent methanol. Units for the slope, plus 0.7894 grams per milliliter. Oops, I forgot. Times X. Our X is percent methanol here. So 0.002 divided by 100. And so this is going to come out to 0.4020 grams per milliliter times my percent methanol, grams per milliliter per percent methanol, MEOH, times my X, which would be percent methanol, plus 0.7894 grams per milliliter.
What was that over there? Is that a plus or a...
That's a plus. Yeah, it's supposed to be a plus. So we could just test this. If we test this, if it's if this mixture is 0% methanol, then 0 times this is 0, and we get a density of this. If it's 0% methanol, then the density comes out to ethanol. If it's 100% methanol, so that would be 100 times this. So we move this 2 over. Move this 2 over, and so this 0.002, the density is going to be 0.002 greater than this, which would be the density of pure methanol. I think. Maybe I made a mistake. Let me double check my calculation. Here. 7914 minus 7894. 7914 minus 7894. No, I guess I didn't make a mistake. 0.002. So it'd be 0.002. Yeah, that's it. So since the densities are kind of close, we don't get that much precision here. You know, we only have 2 sig figs of precision here. But let's try some calculations with this. And so let's try, we could either pick a density or we could pick a percent in solid. Let's pick a density. Let's say this mixture had a density of 0.7900. If the density of the mixture was 0.7900, what is the percent composition? So we just use our mathematical equation here to figure it out. 0.7900 grams per milliliter is equal to 0.020 grams per milliliter per percent methanol times the percent methanol plus 0.7894 grams per milliliter. Okay, then we're solving for percent methanol here. And so I'm going to subtract 0.7894 from both sides. So I'm going to get 0.7900, 0.79 minus 0.7894 equals, and then I'm going to divide it by quadruple 02. So divided by quadruple 02, and that gives me a percent methanol of 30%. Now, how many sig figs am I allowed? Now, I have to keep track of sig figs, so I probably should have done some intermediate step here. And so keeping track of sig figs, the first step I had to do was I had to take 0.7900 minus 0.7894. Okay, this is going to give me 0.0006. I'm allowed 4 decimal places, so that gives me only 1 sig fig. And then I divide that by this, which is 2 sig figs. So I take my 0.0006 divided by quadruple 020. And so now I'm only allowed 1 sig fig. And so all I can say is it's going to be 30% methanol. If it's 30% methanol, then the second equation is it's got to be 70% ethanol. Does that make sense? Okay, likewise, we can just pick a composition and then figure out. Let's say it's 80% methanol. What would its density be? Well, if it's 80% methanol, we'd plug in 80 here and then just solve for the density. We could do it mathematically, or we could do it graphically. If it's 80% methanol, we go to the graph over here, and then go 80% methanol would be about here. And then we go up, and then figure out what is its density graphically. So this is why I call it the graphical method, because we just can use the graph to determine it, or we can break this down into an empirical equation, which is better, and then you calculate using an equation. Okay, does that make sense? And so when you have a 2 unknown problem, one way is you pick the extreme. You pick the extreme 100% one way, and then you pick the other extreme 100% the opposite way, and then you come up with an equation. That's the graphical method. Alternatively, this equation works for everything. Alternatively, we do the system of equations. The system of equations only works for one value. We do it like 80% or whatever, or density of this. So this isn't so precise. The reason this isn't so precise is because the 2 densities are only off by 0.002. These are very small. If the densities were off by a larger factor, then it would be much more precise. And so the question is, assume how precisely could you determine the composition of an ethanol-methanol solution by measuring its density with a picnometer? We can do it to 1 sig fig, unfortunately. Maybe more, depending on, 1 or 2, depending on that subtraction. Assume that the density is a solution of a linear function of the volume percent composition. So that's what we did also. A picnometer CX78 weighs 25.60 grams empty and 35.55 grams when filled with water at 20 degrees C. The density of water at 20 degrees C is 0.9982 grams per milliliter. So we can get the volume. We can figure out the mass of water. From the mass of water, we get the volume of water. From the volume of water, we get the volume of the picnometer. When 10.20 grams of lead is placed in the picnometer, and the picnometer is again filled with water at 20 degrees C, the total mass is 44.83 grams. What is the density of lead in grams per cubic centimeter? So this book is kind of biased towards the density problem because, that's one of the sections there. And so we want the density of lead. The density of lead is we need the mass of lead and the volume of lead. That's why there's so many density problems in this. But we can use dimensional analysis for lots of different types of problems. All right, so we got to figure out how we're going to get the mass and how we're going to get the volume. And so the empty picnometer weighs empty. Oftentimes is abbreviated MT, and it's 25.60 grams. Only 2 decimal places precision. And 35.55 grams when filled with water. All right, so the first thing is let's get the grams of water here. And so the grams of water is equal to 35.55 minus 25.60. And we're allowed 2 decimal places. And so let's see what that comes out to. Just calculate it. 35.55 minus 25.6. 9.95 grams of H2O. Okay, if we have 9.95 grams of H2O, then we can figure out what the volume is using this precise density here, 0.9982 grams per milliliter. And so times 1 milliliter divided by 0.9982 grams for water. And this is going to give us a volume of, so I'll take this divided by 0.9982. The volume is going to come out to 9.9679. Now, I'm only allowed 3 sig figs, but this isn't going to be my final calculation. This is my final calculation. I'd round it. But what I'm going to do is I'm going to just show 3 sig figs here, 9.96 sub 79 milliliters, or round it to 9.97. But I'm going to leave the density the volume like this, because I'm going to use it again probably. 10.20 grams of lead. So we now have the mass of lead, 10.20 grams of lead. And so all we're missing is the volume of lead. That is, how many milliliters of lead do we have? Is placed in the picnometer, and the picnometer is again filled with water at 20 degrees C. The total mass is 44.83 grams. So we're going to have some lead in here, solid, and water, liquid. And the total mass is 44.83 grams. .83 grams. What is the density of lead? So, what do you think for this problem? Well, this is going to be these multiple equations and multiple. So one of the equations we'll say is this 44.83 is the total mass. And the total mass contains, we want the mass of the picnometer. So we need the mass of the picnometer. The mass of the picnometer was 25.60 grams. Plus the mass of the lead, The mass of the lead, well, it's given. How many grams of lead? 10.20 grams. Plus the mass of water. Do we have the mass of water? No. We don't have the mass of water. We don't know what the mass of water is. Can we figure out the mass of water? Yeah. And so let's solve for the mass of water. Which is going to be 44.83. 44.83 minus 25.6 minus 10.2. We're going to be allowed 2 decimal places here. So the mass of water is 9.03 milliliters. 9.030, you know, if I want to carry 1 extra. This is not my final calculation. If I have the mass of water, I can also get the volume of water. The volume of water, I know the density, and so I just I'm going to multiply by 1 over the density. That is, I'll take this number and divide it by 0.9982. And I'm going to get a volume of 9.0463 milliliters. I'm only allowed 3 sig figs in my volume. So I take the mass and multiply by 1 milliliter over 0.9982 grams. That's the volume of water. And the total volume here is going to be the volume of the picnometer. So the volume of the picnometer, or the total volume, is equal to the volume of the water plus the volume of the lead. So we can just solve for the volume of the lead. The volume of the lead is going to be the total volume minus the volume of water. The total volume we calculated earlier, which is 9.9679. And that's going to give me the volume of lead. The volume of lead is 0.92162. 0.92. I'm allowed 2 decimal places, so I'm only allowed 2 sig figs here. 162 milliliters of lead. Okay, once I have that, I can plug that in over here. 10.20 grams divided by 0.92162 milliliters. Let me invert this times 10.2, and I'm only going to get the density to 2 sig figs. So 11.068 grams per milliliter. And since I'm only allowed 2 sig figs, I can round. This is my final answer: 11 grams per milliliter. Yeah, 11 times heavier than water. The Greater Vancouver Regional District, GVRD, chlorinates the water supply of the region at a rate of 1 ppm. That is 1 kilogram of chlorine per million kilograms of water. So they're using it doesn't matter, you can use pounds. 1 ppm could be 1 pound of chlorine per million pounds of water. In this case, they're using kilograms, it's fine. Or grams, we used grams in the last problem. 1 gram of chlorine per million grams of water. It doesn't matter what the units are, the ratio is going to be the same. The chlorine is introduced in the form of sodium hypochlorite. Do you know what the formula for sodium hypochlorite is? Somebody give me the formula for sodium hypochlorite. A lot of people have it memorized because of bleach. Bleach is sodium hypochlorite. Yeah. That's good. What happens if you forget? Well, there's different ways you can do it. you know the series? Hypochlorite, chlorite, chlorate, perchlorate. Do you know all the formulas for those? Hypochlorite is ClO, chlorite is ClO2, chlorate, and perchlorate, and the charge? -1 for all of them. Good. And so they're going to chlorinate it, not with chlorine, but with sodium hypochlorite. And so I'm going to call it NaOCl because that's normally the way it's written. Sodium hypochlorite, which is 47.62% chlorine by mass. I'm pretty sure that's by mass. And so 47.62% chlorine by mass. That means for every 100 grams of sodium hypochlorite, how many grams of chlorine do we have? 47.62. So we're going to have 47.62 grams of chlorine atoms in there for every 100 grams of sodium hypochlorite. The population of the GVRD is 1.8 million persons. If each person uses 750 liters of water, so we have 1.8 million people. I'll just write in exponential notation. And then one person uses 750 liters of water. So that's 750 liters of water per person per day. So per person per day. How many kilograms of sodium hypochlorite must be added to the water supply each week to produce the required chlorine level of 1 ppm? So we want 1 ppm of chlorine. They're saying 1 ppm is 1 kilogram of chlorine per million kilograms of water or solution. All right, you know what this is? This is what we call a two unknown, two equation problem. Because when we add the sodium hypochlorite, it's going to change the volume. And so if it changes the volume, then that's going to change how much chlorine we add. But actually, does it change the number of kilograms? No, it doesn't change the number of kilograms. And then the other thing is sodium hypochlorite a liquid, solid, or gas? It's a solid. You know, a bleach is a solution. They just mix pure sodium hypochlorite with water. And sodium hypochlorite itself is a solid. Do solids change the volume by much? Barely. And so what we're going to do is we're going to make a simplifying assumption. We're going to assume that the addition of sodium hypochlorite has no impact on the volume. Because I don't know what the density of the water is. I'm going to make another assumption. I'm going to assume that the density of water here, because they use 750 liters of water, I'm going to assume that the density is close to 1.0 or 1.00 grams per milliliter. That's what I'll do. And so this is going to be a dimensional analysis problem. What should I start with? $1.8 million people. So I'm going to start with this. This is extensive. So 1.8 million people. And then what should I do? What gets rid of people?
Liters H2.
Yeah, this one. And so I'm going to start off with 1.8 times 10 to the 6 people times 750 liters of H2O per person per day. And so this is going to cancel out people here. this is per day, but they're asking per week. And so what I'm going to do is I'm going to change this. I'm going to change days to weeks. How can I do that?
7 days.
7 days in a week. And so days cancel. And so we need 1.8 times 10 to the 6 times 750 times 7 liters of water per week. That's how much water we need per week. Okay, then I have liters of water. I need to go to what? I need to get rid of liters of water. I want to keep weeks here, but I need to get rid of liters or liters of water. What should I do?
Get rid of liters.
Yeah. Actually, I'm not. We could use the density, but I don't. I'm going to change this because rather than kilograms, I'm going to just go to what's more familiar for me: grams. 1 gram chlorine per million grams of water. This is because I always want to do the density. I don't want to use the kilogram per meter cube. You know, there's another density called kilograms per liter. You heard that one? I don't want to use those. I just want to always use the same density. Grams per milliliter. And so what I'm going to do is I'm going to go from liters of water to milliliters of water. So 1,000 milliliters in a liter. And so the liters cancel, and now I have milliliters of water per week. So now I know how many milliliters of water I need per week. And then here I'm going to have to make an assumption. You know, when you drink the water, you want the water as pure as possible, right? And so we're just going to guess that the density of the water should be about, what? 1.0. We'll just do here. I'm starting to feel uncomfortable guessing it to 3 because guessing it to 3, it's probably more like 0.998, 0.999. We'll just guess it to 2. And so we're going to guess the water is going to be 1.0 grams per milliliter. Now, my given's 2 sig figs, and I really want 3 sig figs here, but I'm kind of uncomfortable getting 3 sig figs here without looking at the table to see what it is. Because the 3 sig figs, it might be 0.998. That was the density at 20 degrees C. In fact, maybe we should use that. Now, if I'm going to go 3 sig figs here, I would go 0.998 and assume the temperature is 20 degrees C. But if the temperature is 25 degrees C, or the temperature is 15 degrees C, that's going to change the density a little bit. So since we have a temperature range, I'm just going to leave it at 1.0. Because do you know what the density of water at 4 degrees C is? 1. Yeah. So if it's really cold in Canada, this is Canada, right? Vancouver. It could be really cold. It could be like 4 degrees, although that would be really, really cold. But some people like really, really cold water. I like cold water. And so it's a little more Dan. So we're just going to go with 1. We can't be too precise here unless we're given a temperature. Then we can be much more precise. And so now we have grams of water per week. And so we want to get rid of grams or grams of water. And here we can get rid of grams of water because we need 1 gram of chlorine for every 1 million grams of water. And so the grams of water cancel, and that gives us grams of pure chlorine. This is the grams of pure chlorine that we need to put in there. Now we got to get rid of grams of pure chlorine, or grams of chlorine. Do we have something that relates grams of chlorine? Yeah, we do. But this takes us in a circle. in a circle, but if we use this, then we get something new. Do you see that one? So let's use this one. And that means we'll have 100 grams of sodium hypochlorite for every 47.62 grams of chlorine. So the grams of chlorine cancel, and that gives us grams of sodium hypochlorite. Do they want grams of sodium hypochlorite? What do they want in this particular problem? How many kilograms? They want kilograms of sodium hypochlorite. So we need one more conversion here. And so we're going to convert grams to kilograms. And so 1 kilogram contains 1,000 grams. Okay, then we're done with this problem. So this is just a straight dimensional analysis problem. So 1.8 times 10 to the 6th times 750 times 7 times 1,000 divided by 1 million times 100 divided by 47.62 divided by 1,000. $1.9845 times 10 to the 4 kilograms of sodium hypochlorite. We're allowed 2 sig figs, so this is going to round to 2.0 times 10 to the 4 kilograms. 20,000, in other words, 20,000 kilograms of NaOCl. Per week. So 20,000 kilograms per week, that's a lot. But it's for 1.8 million people. Where I grew up, they used a lot of chlorine in the water. So when you get a glass of tap water, it just smelled like chlorine. It's heavy. But nowadays, they are using other oxidizers other than bleach.
For the equation, can you cancel out the 1,000 milliliters over 1 liter with the 1,000 kilogram, the 1 kilogram over 1,000 grams?
Yeah, you could do that too. There's ways you could make this shorter, but let's do it.
I can smell the smoke coming off of my calculator. It's so now. I've had this thing since high school.
Oh,
It's taken me far.
that's good. That's nice.
It was the only calculator in the house that could do log.
Okay, you'll need to be able to do logs. Okay, are we good? This one? Well, let's take a look at number 82. I guess I'm spending more time on this. Normally I go through these pretty fast.
Professor, just so I know the structure of the exam, are you going to, or it's the structure of the class, but are you going to be going over homework problems, or are you going to be going over like, kind of like what we did in...
Actually, I'm gonna just primarily do lectures on the topics. Yeah. I'm not gonna go through homework problems. Only for chapter 1.
Okay.
This is because I want to set the foundation. Most of the problems that we're going to solve in the other chapters are going to be dimensional analysis.
Yeah.
So we just want to get good at dimensional analysis.
Okay.
You're going to get.
Since I wasn't here on.
You're going to get.
I have the notes, but
yeah.
you know, I'd like maybe some review, just like different things that.
Mm-hmm.
Yeah.
Yeah. It's not just all homework problems. There'll be more. All right, number 82, a Boeing 767 due to fly from Montreal to Edmonton required refueling. Because the fuel gauge on the aircraft was not working, a mechanic used a dipstick to determine that 7,682 liters of fuel were left on the plane. The plane required 22,300 kilograms of fuel to make the trip. Okay. You know, I always wonder this. I always wonder, you know, when you're at the gas station on a hot day, you know, water expands and contracts a little bit. So the density of water changes. But organics, like gasoline, expand a lot. You know, like I was doing this one lab with acetone, and in the lab was like cold like this, and then it was hot, and then it was cold. You know, the ventilation in the lab was really poor. This is in one of the old like army barracks at UCSB. You know, that's where they threw the lab. You could see the volume of the acetone change during the course of the lab. Is it just expanded as the temperature increased, and then it contracted as the temperature decreased? Now I always wonder. I didn't really worry about this too much, but with gasoline prices this high, I wonder, you know, because I thought, is it better to fuel at night when it's cold or the middle of the day when it's warm? You know, because what's going to happen is the gasoline's going to expand and contract with temperature. So you're measuring how many gallons. Gallons is volume, right? Are you getting the same amount of fuel, as you would at night? You know, at night it's probably more dense. And so it's going to, well, mass doesn't change. You know, if you have a pound, it doesn't matter. A pound of feathers versus a pound of gold, it's the same, you know, weight. And so mass is a measure of how much matter. And so it's much better if the gas pump measured how many kilograms of gasoline you're putting in the fuel tank, because then you don't have to worry if it expanded or contracted. And so I figured, well, I looked at the calibration on the gas pump, and it's calibrated at a certain temperature, so I'm figuring it's by volume. So if it's by volume, then maybe it's better at night, you know, or when it's cold, early in the morning. I don't know. But anyway, this is very dangerous because here they're measuring the volume of the fuel. The volume of the fuel changes with temperature a lot, whereas the kilograms of fuel does not change. So if on the plane they require 22,300 kilograms and you're doing it by volume, that's kind of risky. You know, that's not so precise, and this is why I wasn't so precise here with the density of water, because the density of water changes with temperature. And so we can't be so precise, and fuel is going to be even worse than water. In order to determine the volume of fuel required, the pilot asked for the conversion factor needed to convert a volume of fuel to mass of fuel. Well, the conversion factor is the density. The mechanic gave the factor as 1.77. Assuming that this factor was in metric units, kilograms per liter, the pilot calculated the volume to be added as 4,916 liters. This volume of fuel was added, and the 767 subsequently ran out of fuel, but landed safely by gliding into Gimli Airport near Winnipeg. So this is a true story. The error arose because the factor 1.77 was in units of pounds per liter. What volume of fuel should have been added? So maybe they corrected. Maybe this factor was based on the temperature, you know? And so they looked up the temperature, they got the density. And so maybe it was right. But this is a unit problem. You know, this is kilograms per liter. You see there's no units, so the factor is 1.77. The factor was actually in pounds per liter. What volume of fuel should have been added? So how would you solve this? Yeah, assuming the density is correct, we have liters of fuel, and then we can convert that to mass of fuel. This is kind of a weird density. 1.77 pounds per liter. pounds per liter. So then we can figure out, well, we require 22,300 kilograms of fuel required. And at present, there was 7,682 liters of fuel in the plane. And so what we need to do is we need to figure out how many kilograms this is. And then this is the amount that's required, so the difference is how much fuel we have to add. And so we'll just take this liters of fuel, convert it to pounds of fuel, 1.77 pounds per liter. That gives us pounds of fuel, and then we'll convert it to kilograms. But we're not going to convert it, we're going to convert it to grams because I know the conversion factor, 453.4 grams per pound. That gives us grams of fuel, and then convert that to kilograms. 1 kilogram is 1,000 grams. And so how many kilograms of fuel are on board, assuming this density is correct? And so this must be at the proper temperature, at T, ambient temperature, temperature of the fuel. 7682 times 1.77 times 453.4 divided by 1,000. 6.164, 9 times 10 to the third kilograms, or 6,164, so 9.9 kilograms. So how many kilograms short are we? And so we need, okay, this is going to be 22,300, and we have 6,164.9. So 22,300, oh, I should have just subtracted it, minus 6,164.9 means we're short 16,135 kilograms short on fuel. And so they added, he calculated 4,916 liters. So we're 16,135 kilograms of fuel short. And so what we're going to do is we're going to go 16,135 kilograms of fuel, and then convert that to pounds of fuel. So how many pounds? That would be, actually, let's go to grams. 1,000 grams per kilogram, and then we'll go to pounds. 1 pound is equivalent to 453.6 grams. And that gives us pounds of fuel. Once we get pounds of fuel, then we'll calculate the liters of fuel by using that weird density, 1.77 pounds of fuel per liter of fuel. Okay, so take that kilograms times 1,000 divided by 453.6 divided by 1.77. I get 2.0097 times 10 to the fourth liters of fuel, which is going to be, what is that going to be? That's going to be 20,097 liters of fuel. We're allowed how many sig figs? We're allowed 3 sig figs. So this would be 20,100 liters of fuel. I would feel more comfortable rounding up than rounding down, because if we round this down, then we might run out of fuel. Did I make a mistake?
Under 1 fuel?
I'm sorry?
Was it under liters of fuel? other liters of fuel?
Oh, liters, oops, liters.
Was that under liters of fuel?
Yeah.
What's up there?
Oh, no, pounds per liter fuel?
Yes.
Yeah, that's what was given here. It's a weird unit. It's the factor is 1.77, but it's actually 1.77 were in units of pounds per liter,
Oh.
and so it's just a weird unit for density. And so well, if my calculation's correct, they only added about 4,900 liters. They're way off.
Was that like a fourth of
Is it 453.4 grams per pound or 453.6?
0.6. Oops. It's 453.6.
And would this be expected to be memorized and it's easy?
This one, no. This one I'd give you, but it's common. It's like these two are common, but 3.8785 liters per gallon and 453.6 grams per pound. These two are common. There's an easier one to memorize. The easier one to memorize is 2.02 pounds per kilogram. So this is easier to memorize here, but I've been using this one because Chem 4 uses 454 grams per pound. But you don't have to have it. I mean, if you forget it, it's okay. I'll give that to you. So we know the density changes with temperature, so we've got to be very careful with density. So let's take a look at number 83. The following equation can be used to relate the density of liquid water to Celsius temperature in the range from 0 to 20 degrees C. So do you know where this equation came from? This equation came from observations. And so let's take a look at this is the density of water table, so people just measure the density. So do you know what the density of water at 4 degrees C is? It's right on 1. But when you get to 5 degrees C, it changes. 6 degrees C, 7 degrees C, do you see that?
Yeah.
Okay, these are our observations, and then we look for patterns. Do you know what the pattern is? The pattern's kind of weird for water. And so if we take all this data and graph it, this is what it looks like. Is this linear or non-linear? It's non-linear. And it's hard to see. It's really hard to see because between 0 and 4 it goes up and then drops down. So it's a parabolic curve. It's a parabola. What kind of mathematical equation describes a parabola? A quadratic. And so the mathematical equation for this is a quadratic formula. So somebody figured it out. And here it is. This is the quadratic formula for that equation. I mean, this is the quadratic formula for that curve right here. And so once we describe that curve with a mathematical equation, then we can just plug and chug. That is, we can just plug in the temperature, calculate its density. There are different ways we do this in chemistry. In Chem 4 and Chem 1A, we do something called interpolation. We do something called linear interpolation. So let's say the temperature were 4.5 degrees C. If the temperature were 4.5 degrees C, then I assume that it's linear between these two data points, and I just divide it in half. So the density would be halfway between. Does that make sense? If it's 4.9 degrees C, then it's 9/10 of the way, and we do linear interpolation to figure out what it is. Sometimes we do extrapolation, but anyway, we work with a data table. That's method one. Method two is we just do graphical. So if it's 4.9, I get a ruler, go to 4.9, go up here and figure out what the density is. It's graphical. The best way is mathematical. Just what is the equation for this? And then just plug. So where did this equation come from? Theory? No, it came from observation. Therefore, we call it an empirical equation. This is empirical. This is just the equation that describes that. So let's look at A. To 4 sig figs, determine the density of water at 10 degrees C. So this is temperature in Celsius or temperature in Kelvin? This is temperature in Celsius. We have to always be careful, because the equation for Kelvin temperature will look different. But this is the Celsius. And so if it's 10 degrees C, we just plug that in for T and then solve. So this is just algebra. B, at what temperature does water have a density of 0.99860 grams per cubic centimeter? And so in part B, we plug in the density here and then solve for T. How do we solve for T? We need to use the quadratic formula to solve for T. And so therefore, we have to get this in quadratic form. So we have to have ax squared plus bx plus c is equal to 0. So we're going to have to plug this density in here and then rearrange this equation algebraically to get it into that form, quadratic form, and then plug a, b, and c into the quadratic formula, and then solve for x. That's how we would do this. This is why having the quadratic solver on the calculator is so convenient, because when you look at A, how many digits are you going to have for A? How many digits are you going to have for B and C? Normally when you do this in algebra, it's so simple. 1x squared plus 2x plus 1. The coefficients are really simple. In chemistry, the coefficients aren't so simple. And so when you're punching all those in, b squared minus 4ac, man, it starts getting big. And it starts taking time. And so B, we need the quadratic formula. C, in the following way, show that the density passes through a maximum somewhere in the temperature range to which the equation applies by estimation. So can you estimate where this peaks, Well, when we look at the graph, it's easy. It peaks at 4 degrees. But when you look at the equation, can you tell it peaks at 4 degrees? It's kind of hard. By the graphical method. Okay, the graphical method is just plug in a whole bunch of temperatures and graph it. And then you'll see it peaks at 4 degrees. That's a lot of work. So number 2 is going to take a lot of time. When you look at the solutions manual, how the solutions manual solved it? They measure the density every 5 degrees C. And then they look where it peaks. Nearby where it peaks, then they go to 1 degree C increments. And then they graph it. That's a lot of work. 3, by the method based on differential calculus. Well, calculus is not required for this class, but for calculus, then we can take the derivative. The derivative is like the slope of this, and then we can figure it out. And so these are time consuming, but you could just look in the solutions manual. So I wouldn't actually do these because it's just so much busy work. I just look at the solutions manual and see how they did it. That way, in case something like this ever came up on the test, then I'd have to just bear through it and try to figure it out. 84, a piece of high-density styrofoam, well, you can look at the solutions manual for those. A piece of, for the previous problem, a piece of high-density styrofoam measuring 24.0 centimeters by 36 centimeters by 5 centimeters floats when placed in a tub of water. When 1.5 kilogram book is placed on top of the styrofoam partially sinks, as illustrated in the diagram below. Assuming that the density of water is 1.00 grams per milliliter, so they're going to assume to 3 sig figs what the density is. That's often done. To 2 sig figs you can be pretty confident, but 3 sig figs is only in a very narrow temperature range. But it's okay, it's going to lead to some error. What is the density of the styrofoam? This one, if you look, number 84 is, have you ever seen the concrete boat? Have you ever seen the concrete boat? What's more dense, concrete or water?
Concrete.
Concrete. Should concrete sink?
Not always. If it, you get a pocket of air, it can float. Styrofoam has a lot of air.
So I guess these ships, well, they aren't a great idea, I guess. Somebody's saying a terrible idea. Probably a terrible idea. But why would they float? Why don't they sink? Because concrete's much more dense. It's because of this buoyancy. Are you familiar with buoyancy? This is physics. And when you take physics, you learn that you're going to displace an equal mass. And so if the boat weighs, let's say, 1 kilogram, then you're going to displace 1 kilogram of water, something like that. Do you know that? Okay, so this is not a class on physics. So I probably wouldn't do this. I'd probably just see, okay, how did they do this, and then see, because we're not doing, have you heard of Bernoulli?
Bernoulli principle?
Yeah, Bernoulli and his equation and that stuff. So I'd probably just do that, but we just need the mass and the volume. The volume we're going to get by how much it sinks. But whatever. So 84 I'm not going to worry too much about. 85, a tabulation of data lists the following equation for calculating densities. D of solutions of naphthalene and benzene as a function of mass percent of naphthalene. Okay, so this is an equation that describes how the density changes in this mixture as a function of percent naphthalene, which they call percent N. Use the equation above to calculate A, the density of pure benzene. If we had pure benzene, then we have 0% naphthalene. It's a mixture of naphthalene and benzene. So that's easy. We plug in 0 here, and then calculate it. The density would be 1 over 1.153 grams per cubic centimeter. B, the density of pure naphthalene. Well, that means it's 100% naphthalene. So we plug in 100 here, and then just calculate it. C, the density of a solution at 30 degrees C that is 1.15% naphthalene. So it's 1.15% naphthalene. We plug in 1.15 here, 1.15 here, and then just calculate it. So all those are pretty straightforward. However, the mass percent of naphthalene in a solution that has a density of 0.952 grams. So now if we plug in the density over here, that's 0.952, now we've got to calculate for percent naphthalene. Well, fortunately, this is just a quadratic, so we would use the quadratic formula for D. And so that makes it. Hint, for D you need to use the quadratic formula, so review of the appendix A3. Well, the earlier problem you had to use the quadratic too, but they didn't say this. I don't know, they must have forgotten there. So this is just algebra. That's an empirical equation. The equation that we got, for the ethanol-methanol was an empirical equation as well. 86, so the total volume of ice in the Antarctic is about 3.01 times 10 to the 7 kilometers cubed. Cubic kilometers. If all the ice in the Antarctic were to melt completely, estimate the rise h in sea level that would result from the additional liquid water entering the oceans. The densities of ice and fresh water are 0.92 grams per cubic centimeter for ice and 1.0 grams per cubic centimeter for fresh water, respectively. For seawater, it was like 1.03. Assume that the oceans of the world cover an area of about 3.62 times 10 to the 8th square kilometers, and that the increase in volume of the oceans can be calculated as area times height. So this problem, I was thinking about this problem. This problem, we would have to make some gross simplification to solve this. Because when you look at like an iceberg, you know, I saw a photo of a 200-foot iceberg going past Newfoundland. There's a picture of it recently I saw. And so if we have a 200-foot iceberg here, is that all of it? No. Actually, the bulk of the iceberg is going to be under the ocean, right? And so you're going to have a massive chunk of ice underneath the ocean, which is going to displace the water. So I don't know about this problem because it depends on how, you know, if the Antarctic were floating on the surface, then yeah. If all the ice were floating on the surface, then no problem. We could calculate it because you just calculate what volume that melts to and then just add it. Figuring out the height, you know, like we did all the other problems where we had to figure out the height. And so this is like the dust problem, it's like all the other ones. But because that, you know, in fact, when you look at icebergs, it's probably more like this, you know, the bulk of the ice is underneath. So we'd have to make some pretty gross simplifications to do this. If we make that many simplifications, then let's skip this problem, I think. I mean, we could calculate it, but how accurate of a calculation that would be.
That's what the homework problem is.
Is this a homework problem I signed?
Yeah.
Oh, oops. I assigned, okay, then it must be that I'm wrong with the, let me see what the 10th edition, I wouldn't have signed this. They must have added another problem or two. Need to fix it. Maybe I didn't read it. Skip 86. No. Let me take a look at the 10th edition. Don't have much time. It depends on how, I don't know how the Antarctic ice is. You know, if the Antarctic ice is just on the surface and then it just melts into the liquid, then it's okay. We can calculate it. Three more problems. Dude. An empty 3.00 liter bottle weighs 1.70 kilograms. Filled with a certain wine, it weighs 4.72 kilograms. The wine contains 11.5% ethyl alcohol by mass. How many grams of ethyl alcohol are there in 250 milliliters of this wine? So in this particular problem, we'll have an empty bottle and then an empty bottle filled with wine. This is a 3-liter bottle, 3.00 liters, and empty, it's going to weigh 1.70 kilograms. And then filled with wine, it's going to be 3 liters of wine, and it's going to weigh 4.72 kilograms. so we have the volume and we could calculate the mass. And so we can get the density of the wine. The density of the wine is going to be, I'm going to convert this into grams. So it's going to be 4,720 grams minus 1,700 grams. And so that's going to give us 3,020 grams of wine divided by the volume, which is 3,000 milliliters of wine. And so I just did the conversion in my head. And so what does that give us for the density? $30.20 divided by 3,000. 1.006 grams per milliliter. So very close to water. The wine contains 11.5% ethanol by mass. So 11.5% ethanol, ETOH, by mass. So that means 11.5 grams of pure ethanol for every 100 grams of wine. How many grams of ethyl alcohol are there in 250 milliliters of wine? So if we go 250 milliliters of wine, that's our given, then we need to get rid of milliliters or milliliters of wine. Actually, we can get rid of milliliters of wine because we have the density of the wine here. And so for every 1 milliliter of wine, we have 1.006 grams of wine. And so that gets rid of milliliters of wine. It gives us grams of wine. And then we can just go to grams of ethanol. So this, I don't know, does this seem like a challenge problem? 11.5 grams of ethanol per 100 grams of wine. Grams of wine cancel. That gives us grams of ethanol. So this doesn't seem like such an advanced problem, does it? That seems like a basic problem, so I'm surprised it was in this section here. 88. The filament of an incandescent light bulb is made from tungsten metal, which has a density of 9.3 grams per cubic centimeter, that has been drawn into very thin wire. The diameter of the wire is difficult to measure directly, so it's sometimes estimated by measuring the mass of a fixed length of wire. If a 0.200 meter length of tungsten wire weighs 42.9 milligrams, then what is the diameter of the wire? Express your answer in millimeters. So this problem is very similar to the earlier problems, except we're solving for the diameter. And then there's going to be a length here. We have 0.200 meter length. Earlier we were solving for the length. In this case we're solving for the diameter. But anyway, it's the area times the length, which is going to give us the volume. So when I look at this problem is just the same as the earlier problem, except we're solving for a different variable. Does it look like it? Pretty straightforward? Yeah, that's pretty straightforward. So I'm going to skip it. 89. Are we at 50 or 55? 50? Oh, I guess we're out of time. 89. This is the only chapter I'm going to go through all these problems. But we're going to finish with 89 here. That's the last problem in the advanced section. We'll do that tomorrow. I was supposed to give the quiz, but I'm going to have to postpone the quiz till tomorrow.